Hello, good morning. Myself, Dr. Lakshmi Devi, Professor, Department of ECE, St. Peter's Engineering College. I would like to discuss here image restoration concepts. Image restoration differences between restoration and enhancement. First, let us start. What's the syllabus given the digital image processing as a third year, second semester subject of DIP under JNTUH? Image restoration consists of degradation model, algebraic approach to restoration, inverse filtering, least mean square filters, and constrained least square filtration or constrained least square restoration methods. These are the topics given in your syllabus of digital image. Now, what are the main contents we'd like to discuss in this particular session? Total image restoration means, first, differences we can see, restoration and enhancement, then degradation model, algebraic approach to restoration. In the upcoming videos, we'll see inverse filtering, least mean square filters, and constrained least square restoration concepts. Now, first, what is image restoration? So, while observing these two figures, we are in a position to observe the first figure is affected with some noise, and second figure, as compared to the first figure, having better clarity as well as the quality, you can say. At this particular moment, I would like to specify how this quality of an image is extracted from this particular noisy image. That is through a restoration process. Restoration or restoration, will call it as restoration, image restoration. When you'll go for the restoration, when you'll go for the image enhancement, but both the processing output is extracting of a quality from the degraded quality of the images. So once we have an input which is noise affected images or degraded quality of the images as an inputs, extracting the quality of the degraded images through these processings, either enhancement or restoration, we'll call it as actually improving the quality of an image. But these are the two methods for improving the quality, but difference should be there, and evaluating of quality of an image through enhancement as well as quality of an image through restoration. In the enhancement techniques, we never bother about the reason for degrading the image or identifying the reason for degrading the image. But while coming to this restoration, it's very essential to identify the reason for degrading the image at its input. Once you identified the reason for degrading the image at its input, then we can take proper measure in the reverse manner in order to retrieve as best as or as close as original image with improving quality. We'll call it as image restoration. That means identifying the reason for degrading the quality of an image, and by applying reverse mechanism for retrieving it back to the maximum extent with the improving of quality, we'll call it as image restoration or restoration. Then, image restoration attempts to restore images that have been degraded. This is one of the definitions you can say. Attempts to restore images that have been degraded. Let us observe in this particular example. Left side we have degraded image and right side a restored image. So identify the degradation process and attempt to reverse it. Almost similar to image enhancement but more objective. These two sentences are very abstractive in nature for defining of image restoration. The thing is, with the human eye, while observing with the degraded images, we are in a position to identify that image has corrupted with some noise. But what type of noise it's actually affected means, while observing the image, we are in a position to identify the noise is periodic. That is, the noise comes under the periodic noise type. Because it's not actually the randomly distributing some disturbance. It's some periodic disturbance is appearing in the images. That's the reason we'll call it as some periodic noise added in the images which appears to be degraded the quality of an image. If you apply this particular image and extracting the quality image through a particular methodology in the restoration process, that particular image we are denoting it as restored image. That means the periodic noise which is affected at the input image, we are minimizing it and extracting the qualitative image that we named it as restored image. This is a small example we can observe here, how we can use the restoration and what type of results we can extract from the degraded image quality to the improved quality image at this out. Now, restoration improves image in some predefined sense. It is an objective process. So here you should remember one point regarding the image enhancement and restoration. Image enhancement is an actually subjective process. Image restoration is an objective process. This, while starting with the image enhancement also I specified there, image enhancement is a subjective process and image restoration is objective process. Here we should have certain fundamentals or certain mathematical models to prove or to improve the quality of an image. That's the reason restoration is an objective process and enhancement without having any such particular mathematical proofs. We are extracting the quality of an image in the image enhancement. That's the reason image enhancement is the subjective process and image restoration is an objective process. Then, restoration attempts to reconstruct an image that has been degraded by using a prior knowledge of the degradation phenomena. So in this, already I told you, reconstructing mechanism is there based on the type of degradation that input image undergone. Based on the type of degradation, we are applying the reverse mechanism of retrieving it back as close as possible to the input error-free image. We'll call it as image restoration. That's the main attempt to do in the restoration process for reconstructing an original image with improving of quality. These techniques are oriented toward modeling the degradation and then applying the inverse process in order to recover the original image. There are a lot of tasks in image restoration. Let's talk about three main tasks in image restoration. The first one is denoising and general reconstruction. Denoising and general reconstruction. That means once the image is affected with the noise, whatever the methods we are applying through this image restoration process, our main target at that particular moment, denoising the original image, then definitely the improving of quality we can observe on processed images. Then with the general reconstruction mechanism, if you have used some sort of filters, there is a chance to have minimizing of such noises. Either it may be at the time of encoding process or at the time of transmission process, there is a chance to have noise to be added to the original images that will be minimized, or reconstructing the image with improving of quality through minimizing of these noises comes under this particular task. That's a denoising and general reconstruction. Image denoising refers to an attempt to restore images contaminated by additive noise or sources such as compression. While using the compression also on images, there is a chance to have some sort of noise to be added for this particular compression process. That particular noise also to be minimized with this particular denoising concepts in the image restoration. Let us see here one example. With this example here, you can observe first image is affected with some noise. That's the reason it doesn't have any quality and clarity also in the first image. But while observing this in the second image, the total noise gets minimized. This is the best example of denoising concept with the general instructions or general process of using filters, how you are denoising the image. Noise have been removed and original image appears to be like this with improved quality as compared to the input degraded image. Second one, super resolution concept. Task is super resolution. That is, the main goal of super resolution is to take a low resolution image and upsample it to create high resolution version. Already we come across in the first unit, the basic introduction parts, what are the different types of resolutions we have and how we are improving the resolution either on spatial resolution or gray level resolution. So in any of these cases, is there any chance to have input images less resolution image, and based on the concept of either spatial resolution or intensity resolution, if you have improved the quality of an image, that concept will call it as super resolution concept. That is, number of dots per inch, we can specify it as the spatial resolution. Number of bits per dot, we can specify that intensity resolution or gray level resolution. If you are increasing the number of dots per inch, we'll call it as an actually the spatial resolution to be increased with which may help for improving the quality. With increasing the number of bits also, it improves the quality of an image. That particular concept we'll call it as super resolution for improving the results. Just you can observe here, two images are there. Fruits, fruits images. The first image is low resolution image and second image is high resolution image. By observing with our human eye, we are in a position to identify the difference on its quality regarding the first image and second image. Second image have the clarity of vision as compared to the first image. That is, that shows actually the resolution problem, low resolution to the high resolution. Such a way, if you have input image and if you have improved the resolution of the input images, we have this high resolution of images. That also happens through this particular restoration mechanism. Coming to the next one, image in painting. This is the third concept. The main three tasks. Third one is image in painting. Is the process of reconstructing lost or deteriorated parts of images and videos. Might be come across here and there. For the last 20 years back, 30 years back captured images at our homes, degrading the quality of an image. That type of images, if you have submitted or if you have given to the Photoshop, that people can reconstruct that particular damages in the images and they can develop a new image which should show a better quality as compared to the original image. That particular technique we'll call it as image in painting. This technique is often used to remove unwanted objects from an image or to restore damaged portions of old photos. Just see this particular image in painting. This image is an actually for the last 40 years back, 50 years back captured image. It is totally deteriorated its quality with so many rashes or so many lines over it, which degraded the quality of an image. Through this image in painting concept, we can reconstruct that particular image to this level. That is also happens through this restoration methods only. That process will call it as image in painting concept. Next, image enhancement or restoration. Small sort of differences here we can observe. Most of what we learned in image enhancement chapter can also be classified as image restoration techniques. Some of the techniques which we offered in the enhancement, we can use the same techniques in the restoration also. The reason is both the process main aim is improving the quality of an image. But In this specifically, linear filtering, that is low pass for noise reduction, high pass for edge sharpening. Linear filtering concepts you can use for the low pass filters for the noise reduction and high pass filters for edge sharpening, and also band pass filters we have, band reject filters also we have. Based on this many different types of linear filtering concepts, if you are focusing on removing the specific band of frequencies, either it may be a lower range of frequencies, or it may be higher range of frequencies, or allowing a specified range of frequencies, or rejecting a specified range of frequencies, we'll call it as low pass, high pass, band pass, and band reject filters. That type of linear filtering concepts are there. Then median filtering concepts, for a specific type of noises, we are focusing on median filtering concepts. That median filtering concepts, median for salt and pepper noise, log domain filtering, and other non-linear techniques we have. So this all the filters we can see in this particular filtration concepts. Image degradations. So now image degradations means what are the reasons for having degrading the quality of an image? Means motion blur, focus blur due to resolution problems. There is a chance to have degrading the quality of an image. So for retrieving these particular degradations, we have different types of filters. That filters will call it as inverse filters, Wiener filter. In contrast to image enhancement, image restoration, the degradation is modeled. This enables the effect of degradation to be removed. Degradation to be largely removed. With this particular degradation mechanisms, once we identified the reason for degrading the image, and by applying the reverse mechanism, we can minimize that effect and maximize the improving the quality of an image. Let us see here motion blur. If it is motion blur means what type of effect? It appears on input images. If it is a focus blur, what type of effects? And the resolution already we observed. Based on low resolution, how the image appears to be degrading the quality of an image. So let us here you can observe. First figure is original image. Second figure optical blur. Due to the blur, actually that image is degrading the quality. That blurriness will call it as an optical blur. Then the third figure is a motion blur. And fourth figure is a spatial quantization, that is discrete pixels. Spatial quantization problem regarding spatial locations. If you have any discrete pixels problem, then that appears to be some sort of noise here. Then additive intensity noises. Is there any salt and pepper noises added in the original image? That image appears to be like this. These are the different types of degradations in general we can observe in the images point of view. Basically, if you come to this particular slide and its explanation, types of image degradations. Blurring, noise. Types of image degradations basically can divide into degradation due to blurring and degradation due to noise. These degradations basically we can categorize into the two ways. One is degradation due to blurring and degradation due to noise effects. Then again, the blurring can be divided into the three types. That is, the reason for occurring blur into the images. One is motion blur. Either maybe a cameraman is moving or maybe a scene is moving. On both the cases, the motion blur effect occurs on captured images. Second one is lens blur. So cameraman, if they didn't adjust properly the lenses at the time of capturing an image, definitely there is a chance to have some sort of blur appears on captured images. Without having proper adjustment of the lens, if we have such a problem of blurriness, that we'll call it as lens blur. Then each and every cam, based on its quality of perception or quality of capturing, It's have its own quality, 12 megapixel, 24 megapixel, 32 megapixel, like that. So each and every camera have the point spread function. If the point spread function having some sort of any problem due to age or due to the service or due to the manufacturing mix, there is a chance to have some point spread functions gets vary based on the service or based on the duration or based on lifespan of that particular cams. Then definitely that effect also leads to some sort of blur on captured images. That we'll call it as due to cam point spread function that leads some sort of blurriness. These are the maximum cases for occurring blurred into the images. One is motion blur, lens blur, third one is due to point spread function of the cameras. Then, so in this, what are the different methods we have for estimating this particular point spread function of cams? Those mechanisms we'll call it as basically image by observation. By image observation is one method of estimation of point spread function. Second one is by experimentation. Third one is by mathematical modeling. That means for identifying the blurredness which occurs through a point spread function of a cams, there are three ways to identifying the blur or identifying the reason for degrading the images. That is by image observation, second one is by experimentation, third one is by mathematical modeling. This itself shows and actually how we are going to demonstrate image observation. That means if you identify any of the system or any of the character is degrading his quality or degrading his character, if you want to set right that particular character or system, definitely we need some strategy for retrieving it back to the original state without having any problem to that particular either character or a system. What type of measures you can take for minimizing that effects means the first one is here, image observation. By observing the images, how this particular images can respond based on the different situations of capturing and different atmospheric conditions of the capturing. Accordingly, we can identify that particular behavior that we'll call it as image observation. On that particular instant of time, during that particular period of a season or period of a time of a day, if I have captured the image, then definitely that effects appears on capturing of images. That observation can give some sort of information, reason for degrading the quality of an image. Then by experimentation. So through this experimentation, would like to observe whatever the mechanism they have used at the first time of capturing of an image, the same type of mechanism we can use once again during more or less the same circumstances of the atmosphere. Then still if we have the same type of quality captured by the same cam, that itself indicates the problem with the cam only. Suppose there is no any sort of difference might be observed from the given input image to through experimentation, whatever the image you have extracted, that itself indicates your point spread function is an actually functioning properly as compared to the input image to the second time captured image. But this experimentation leads to a different atmospheric conditions, how to maintain the data, and finally you come to one conclusion. These are the reasons for degrading the quality of an image or estimating the point spread function of a given cam. Then by mathematical modeling, we have to take care of at a different circumstances, different mathematical equations and getting solutions for those, and then gives the theory of reason for degrading the quality of an image with some mathematical proofs on paper. That mechanism of estimating the degradation, we'll call it as mathematical modeling. These are the main 3 points for estimating the point spread function or estimating the degradation occurs on input images. Then coming to the noise here on right hand side, noise, that is degradation due to noise. Again, that will be divided into the two types. One is due to electronics of cam. Due to electronics of cam means cam definitely consists of so many operations occurs at the time of capturing. That is converting of physical energy into electrical energy. That is basic photodiode principle is occurs. In this particular conversion, there is a chance to have for some sort of energy conversion gets taking place, a photon energy into electrical energy, then there is a chance to have some sort of noise to be added in this particular process. That will call it as due to electronics, there is a chance to have introducing some sort of noise in the conversion process. Then due to quantization problem. So, you know what's meant by the sampling and what's meant by the quantization. During that quantization process, is there any chance to have in the digital cameras or charged couple devices some sort of noise to be added in the original images? That basically these are the two reasons for noise to be added into the input images. Then what are the different models of noises we have based on this PDF of the noise models? Probability density function of noise models. What are the different types of noise models we have? Totally the noise models have been categorized into the two types. One is random noises, second one is periodic noises. We have different types of random noises, but under the periodic, basically a sinusoidal and a cos. See here in the last information just here, noise models, there are 6 types of random noises and periodic noise. Random noises are 6 types and 1 periodic noise. These are the different types of noises. So in this, what are the different filters we can use and how to minimize them? Such type of noises means atmospheric turbulence models, ideal low pass filters, and as well as practical low pass filters. Under practical low pass filters, we have Gaussian low pass, Butterworth low pass filters, and linear motion blur models. These are all comes under minimizing of some sort of random noises. So random noises like gamma noise, long noise, exponential noise, logarithmic noise, uniform noise, impulse noise. These are the different types of random noises we have. For these noises, each one have its own filter mechanism of minimizing that types of noises present on original images. Okay, then direct inverse filtering concepts we have for this particular all types of filters in frequency domain. Okay, in frequency domain, we have different direct inverse filtering concepts. The direct inverse filtering concepts we'll see in the upcoming videos. Now coming to the periodic noises, that means a restoration of noise, restoration due to noise only if we have, without having any other degradation mechanism. Then what type of methods we can use for minimizing of those? That means spatial based method filterings and frequency based methods. These are the two different types we have. That is, whenever noise is present in the images, that is spatial based method filterings, how we can make use of it. Under the spatial based method filtering, mean filters, statistical based filters. Under the mean filters again we have some types. Those are arithmetic mean filters, geometric mean filters, harmonic mean filters, contra harmonic mean filters. Statistical based filters are again divided into 4 types, that is median filters, max or mean filters, midpoint filters, alpha mean filters. These are different types of statistical based filters under additive noise if it is present. That is a spatial based method filtering concepts. Coming to this frequency based methods, periodic noise to be removed by frequency based methods, random noise to be removed by spatial based methods. Just to remember one more point here as image restoration, when you can prefer the spatial based filtering methods and when you can prefer the frequency based methods for minimizing of noises means, for random noise minimization we can use spatial based filtering methods. For periodic noise minimization purpose we can use periodic noise minimization purpose we can use frequency based methods. Like this, these two methods are meant for its own reasons for minimizing the affected noises on a given input images. Under this periodic noise reduction concepts, we have three basic types of filters. Those are band reject filters, band pass filters, notch filters. So band reject and band pass filters by itself explains what is the meaning of calling these filters are band pass and band reject. Notch filters again, which allows a specific frequency, notch pass filter will call it as, which rejects a specific frequency will call it as notch reject filters. Like this, we have different types of filters. Coming to this, algorithms that incorporated degradation due to point spread function and noise. In the last slides, we come across what are the different hierarchy of degradation mechanisms and retrieving of that degradation methods we come across due to point spread function separately and due to noise separately. Suppose if the image is degraded its quality due to combining of these two reasons, that is point spread function of the cams as well as due to additive noise, if the image is degrading its quality, then what are the different algorithms it's incorporated for minimizing of that degradation? We'll call it as, basically there are two types of filter mechanisms. One is minimum mean square error filter. That another name for the minimum mean square error filter is Wiener filter. Then the second one is constrained least square filtering. Constrained least square filtering. These are the topics we have in our syllabus of image restoration, a total unit. These particular topics in depth we'll discuss in the next videos. Minimum mean square filtering, constrained least square filtering concepts. But what's the basic difference between these filterings? Just I'll give here. Minimum mean square error filter requires a knowledge of the original undegraded image power spectrum and of the power spectrum of the noise. That is, power spectrum of the original or undegraded image as well as power spectrum of the noise it requires in case of minimum mean square error method. Just to remember the difference between the minimum mean square error method and constrained least square filtering concepts. In the minimum mean square method or Wiener filter, it requires the power spectrum of the image, original image, as well as power spectrum of the noise. But in constrained least square filtering concepts, it requires only the mean and variance of the noise. It requires only the mean and variance of the noise. That is a mu and sigma square of the noise terms. No need to have any power spectrum of the noise. But to be frank, evaluating of power spectrum of a noise is very difficult task in order to identify the main filtering mechanism or extracting of a qualitative image through this particular minimum mean square filtering. It's very essential to have power spectra of the noise as well as power spectra of the signal. That is nothing but original or undegraded image power spectrum. as well as power spectrum of the noise. But there is no need to have that power spectrum term in the constrained least square filtering. It needs only mean and variance of the noise. Based on the type of noise, you can calculate what's the mean of the noise and what is the variance of the noise. With these two statistical parameters, we are in a position to identify the constraint least square filtering concept and reconstruct the image for improving the results. Under this minimum mean square error method, a geometric mean filter, that is a generalized form of a Wiener filtering, also called the spectrum equalization filter. This is also another name for that particular Wiener filter, spectrum equalization filter. So geometric mean filter means a generalized form of Wiener filtering, also called the spectrum equalization filter. So these are about the minimum mean square and constrained least square filtering concept. Let us see here the general model of representing the degradation and what are the various models of representing the degradation and the degradation model system we can observe now. In general way, representation of this particular degradation is g of xy is equals to t of f of x. So that's a transform operator t of f of xy plus n of xy. T of may not be a linear. That is a transform of input image f of xy may not be a linear function. But what it indicates, g of xy is a degraded image, f of xy is the original image, and n of xy is an additive noise. Then modeling t of by a filtering operation. Whenever you can use the filtering operation in this particular degradation models, a degradation system mechanism, that we are representing it as g of xy is equals to f of xy convolution of h of xy. H of xy is actually degradation filter h of xy. F of xy is an input image plus n of xy. This means that the degradation operator is linear and shift invariant. Degradation operator is linear and shift invariant. H of xy is unknown and needs to be estimated, that is system identification problem. Once you have estimated that particular h of xy, you are in a position to evaluate the degraded image g of xy with a convolution of f of xy with h of xy plus n of xy. Once you know this particular f of xy convoluted operation with the h of xy and additive noise, then you have degraded image g of xy. Then h of xy and some statistics of n of xy. How to recover f of xy from a g of xy. That is, once you have the degraded image g of xy, once you have a degraded image means that itself indicates g of xy. Suppose if you have any information regarding this particular degradation concept of h of xy and degradation concept of a noise n of xy. N of xy, h of xy you know, and g of xy is the degraded image we have, then we are in a position to recover or reconstruct f of xy from these particular informations. To estimate h of xy and statistics of n of xy, what are the different that we will see here? Degradation due to finite size sensor. That is, degradation happens in the images due to finite size sensors. Ideally, the value of a pixel should be the light intensity at an infinitesimal point in the imaged sense. Each sensor in a charged coupled device array integrates the light intensity in a small area surrounding a point with possibly non-equal weighting. The point spread function is the image captured when there is only one single point with high intensity in the scene. This point spread function is the degradation filter. See here, h of xy due to sensor point spread function is a low pass and is often approximated by a Gaussian filter. That is h of xy for the given degradation filter. H of xy is equals to exponential of minus k x square plus y square. So let us observe these two images here, that is degradation estimation by impulse characterization. Figure A is an impulse of light. This is a magnified form of light. So whenever we can capture that image, that is image after capturing, definitely that light is an actually degraded its quality. That appears to be image impulse, that is degrading the quality of a light which appearing in the first image. If you have observed the first image to the second image, that light is spread around it, that particular thing will call it as an actually degrading the quality of exact impulse of a light which is appears a magnified form in the first image. That is also one sort of a nice or degrading the quality of an image as compared to the first image. The sensor integrates the intensity value of a point over a certain exposure time t. When there are moving objects in the imaged sense at high speed relative to exposure time, we see motion blur gets taking place. To reduce the motion blur, one can reduce the exposure time. This is actually the conclusion for regarding minimizing this particular blurriness in the images. In order to reduce the motion blur, we can reduce the exposure time, then automatically the motion blur gets minimized. Whenever moving objects are there, or moving scenes are there, or moving camera is there, there is a chance to have some sort of blurriness appears, that definitely we can observe due to this motion blur. This is an example of a motion blur here. Original image is the first image, second image is result of blurring using this particular function of equation, that is due to a motion blur. Definitely you can observe either screen or the cameraman is moving. Because of that, we have this type of quality of an image. This is due to a motion blur with the probabilities of indication A is equals to B is equals to 0.1 and is okay. So I hope you understand the reason for entering to the restoration. What are the different restoration methods we have, a reason for degrading the quality we have based on the spatial domain as well as frequency domain. What are the different degradation chances we have, then combining of both, that is due to degradation mechanism as well as due to noise. If the image is affected and degrading its quality, then what are the main methods we have for retrieving the image as close as possible to the original image? That's the main aim of image restoration. I hope you understood this introduction part of image restoration. In the upcoming videos, we'll continue the remaining filters as well as a minimum mean square filter or Wiener filter and constraint least square filter in the upcoming videos. Thank you.